show you guys that a little bit? Maybe just a little bit. Okay, when I look at a rational function, I always approach it from the front, and I want to see it as a polynomial over a polynomial because it tells me so much. Guys, when you look at this, when you see like a linear function on a linear function, polynomial over polynomial, when you approach it from the front and you see that the degree on top is the same as degree on the bottom, your horizontal asymptote would be y is equal to a over c. Do you see it? Okay. And then down here, I know that cx plus d can never equal 0. So then x can never equal negative d over c. That means my vertical asymptote would be negative d over c. Do you guys see it? Okay. And then we know that this is polynomial over polynomial. If I make my x's zeros, then my y-intercept becomes that quotient. So for y-intercept, that's where x is equal to 0. It would just be b over d. Do you see it? Okay. And then the last one, if I say x-intercept, right away, when we say y is equal to 0, and I have ax plus b over cx plus d, and I multiply by 0, the bottom factor does not weigh in at all to the x-intercept, right? And then we would have this, which would be negative b over a. And if you actually look at it as a polynomial over polynomial, I always just kind of like approach it from the front, and I kind of create my box. And I look at it from the front, and then I work my way around, and I make sure I got all those values. But your math can justify it too. Like you can substitute the 0 in for the x's so you can see the b over d, right? And it makes sense that for polynomial functions, if my constant term is the y-intercept, then it would make sense if I divide those y-intercepts, then it's going to be the quotient for the new y-intercept, right? So I totally messed up that last example with the first one I gave you because it actually wasn't a vertical asymptote. It was actually something called a point of discontinuity, and we're going to talk about that in a second. But I hope this feels entirely comfortable to you. Now, there's going to be times when they don't give it to you as a polynomial over a polynomial, and it's rare, but it does happen. If you're looking at it in transformation form, there wouldn't be a stretch factor that would be a b value, so there's not going to be a b stretch. There's just going to be a vertical stretch and a possible reflection across the x-axis, and then an x minus h on the bottom, and then a plus k. The vertical asymptote is still going to be determined by the non-permissible value for x. So x equals h, which is the horizontal translation, is your vertical asymptote. Sorry, horizontal. I've got the words mixed up, don't I? No. X minus h can never equal 0. X can never be h. That's vertical asymptote. Horizontal translation, vertical. Sorry, just wasn't reading the whole thing. Horizontal translation gives you the vertical asymptote, and then the vertical translation will give you a horizontal asymptote. I don't like seeing a function in transformation form because I really love seeing polynomial over polynomial, okay? So when I'm looking at this guy, like if you were given this, y is equal to 3 over x minus 2 plus 5, and you were asked to work with this function, it was so easy for us to graph those other functions. Like, why wouldn't I want to make this look like polynomial over polynomial? So I can see that this is a vertical stretch by a factor of 3 from the x-axis. This is a horizontal translation right 2. So h is just always attached to the x wherever the x is. And then k is always that lost number, that vertical translation up 5. But if I wanted to graph this, I would just get a common denominator here. And I would make it look like a polynomial over a polynomial. And I would make it look like, so I can kind of approach it from that box method. So if you see a transformation form of a rational function, just change it into polynomial over polynomial. So this becomes common denominator of x minus 2. There's my denominator. And then I've got 3 plus 5x minus 10. And my new function would be 5x minus 7 over x minus 2, horizontal asymptote, y equals 5. Vertical asymptote, x equals 2. Y-intercept, 7/2. X-intercept, 7/5, right? Putting the 0 over here, and I can see it all. So you don't have to work with the transformation form. You can turn it into a single, like polynomial over polynomial, single fraction, okay? But it's kind of handy for you to know how to develop this equation as well. So it says write the equation of each function. If you're going to memorize anything, you need to know that your x equals h is your vertical asymptote, and your y equals k is your horizontal asymptote. And there's always the potential for an a value. So here it says horizontal asymptote, y equals 0. Remember that when you're thinking y's, you're thinking k's. Vertical asymptote, you're thinking h's. Because that's an x equals, you're thinking that changed the h. So those are your zeros, and if I wanted to come in and find the a value, it'd just be as simple as finding whatever the stretch factor was. That's not a function yet. How do I make it a function? I use a given ordered pair, and I algebraically determine the a value that's going to force it to go through that given ordered pair. And so I have 1 is equal to a over 3, and I can see that a is equal to 3. So I should put 3 in. This is my function right here. And that would be in transformation form. Okay? So all you really need to remember, there isn't going to be a b value for your rationals. So y is equal to 0. That means your k was 0. X is equal to 5. That means your h was 5. And your transformation form looks like this. The h always just follows the x wherever the x is. And your vertical stretch would just be on top here. So right away, I know my h is 5. I'm not going to put the plus 0. Are you guys okay with that? Okay. And if I'm going to algebraically determine the a value, I've got 6 and 2 as a given ordered pair. There's my x and my y. So 2 is equal to a, and then 6 minus 5, which is just going to be 1. So 2 is equal to a. This is my equation. So I could describe the transformations as being a vertical stretch by a factor of 2 from the x-axis, and then a horizontal translation, right 5. Okay, and if you think about it, your most basic function had a vertical asymptote at x equals 0, and then a horizontal asymptote at y equals 0, and we've just moved them around. That's our transformations. Again, the horizontal asymptote, that's a y value. That's going to be affected by k. That's going to be my k value. This is an x value. X's are altered by h. So right away I know my k and my h. And then when I plug into my transformation form, that would be left 4. And I don't need to put the 0 in. Pick a point. So -5 and 2. And algebraically determine the a value. If you were to describe the transformations on this, you would say reflection across the x-axis. Usually, if you don't have a reflection across the x-axis, guys, we're usually bottom left, top right. It's kind of like a positive slope, but this is actually top going down. Like, do you guys see like it's like left to bottom right? It's kind of going down. That's what a reflection across the x-axis would look like. So I would describe this as a reflection across the x-axis, a vertical stretch by a factor of 2, and then a horizontal translation left 4. And that's why we have this x equals negative 4 horizontal translation. Are we okay with these? Okay. We've been seeing transformations for so long that really it's just knowing where the h and k land in a different function. Okay, so it says a rational function y is equal to a over x minus 5 plus k passes through the points 6 and 7 and 4 and 1. Determine the values of a and k. Guys, if we've got two unknown values, you need to think about your grade 10 skills. What grade 10 skills did we develop that helped you find two unknown values? Do you guys remember? You've got two unknown values. You're going to have to create a system of equations, okay? So when you think two unknowns, I need you guys to think system of equations. And when you're thinking about a system, I need you to think either substitution or elimination, okay? So if you've been gifted with two ordered pairs and you're looking for two unknowns, you're going to create your system. So when I look at this function, we have 6 and 7. That's a possible x and a y. I also have, I'm going to use a different color. I also have the 4 and the 1, which is an additional x and y. So I'm going to plug my 6 and 7 in and just see where it takes me. So if this is my equation, y is equal to a over x minus 5 plus k, substitute the 7 in for the y, the 6 in for the x. Now 6 minus 5 is 1. Are you guys okay that we would just stop right here? I have no idea what a could be 1, k could be 6, a could be 2, k could be 5, right? Like there's so many opportunities here. I don't have enough information to definitively decide. So now I go to the other ordered pair. So y is equal to 1. And then I've got 4 minus 5. And then I've got my plus k. 4 minus 5 is negative 1. So a divided by negative 1 would be negative a. Do you guys see that? Like that would be negative 1 on the bottom. A divided by negative 1 is just negative a. And then if you look at this carefully, you should be able to see like, holy smokers, this is like a perfect situation for elimination. If I put the 1 and the negative a and the k right on top of each other, if I add straight through, I get 8 is equal to, the a's cancel, and I get k is equal to 4. Yeah? And if k is equal to 4, pick whichever one you want, right? Like I'm going to grab the green one actually, because I like 7 is equal to a plus k. So 7 is equal to a plus 4. A is then 3. Okay, we're going to graph the function, but I'm actually going to write it as a single rational function first. So when I put all the details together, we've got y is equal to, my a value is 3, I've got x minus 5, and then my k value is 4. I don't like graphing this. It doesn't seem intuitive to me. I like it better when it's polynomial over polynomial. So right away, I'm going to write this as a single fraction so I can see my polynomial over polynomial so I can get all my critical features. So you're finding a common denominator, and on the top I've got 3 plus 4x minus 20, and I put my like terms together. And then I can grab horizontal asymptote. the horizontal asymptote, y equals 4. Vertical asymptote, x equals 5. And it kind of should, like, it should make sense. Like the k value was the 4, and the h value was the 5. And then my y-intercept, and I'm just using my box method. I'm approaching it from the front, and then I took the bottom. My y-intercept is going to be 0 and 17/5. Negative 17 divided by negative 5 if these are zeros. And then my x-intercept is going to be 17/4 and 0. If you want to see the math, it's 4x minus 17 all over x minus 5. This becomes 0. And when I solve for x, it's 17/4. Do you guys see it? And it comes from the factor that's on the top. I prefer this polynomial over polynomial to transformation form. But if you wanted to describe it, you would describe this guy. So our final answer here was y is equal to 3 over x minus 5 plus 4. Vertical stretch by a factor of 3 from the x-axis. Horizontal translation, right 5 units. Vertical translation, up 4. We have y equals 4, x equals 5, needs to be clearly labeled. So y equals 4, label it as equals, not an NPV. X equals 5. Zero and 17/5, that's like 3.4, right? So I'm just going to find 3.4. Here's my y-intercept. And then I've got my x-intercept was 17/4, so that's like 4.25. Okay. Make sure you're going through. So I should actually label these. This is 0 and what was it, 17/5. And then this one was 17/4 and 0, right? Get infinitely close to the asymptotes. Do not cross them. If you cross that asymptote, we're in trouble. Don't forget that no matter what, we're going to have to come up with a graph on the other side. No matter how small or big your graph is, you still have to show me that there was something that happened diagonally across where the asymptotes intersect. Guys, what's the ordered pair where the asymptote intersects? Like, that could be a question. Hey, where do the asymptotes intersect on this rational function? What would that ordered pair be? Simon, what would that ordered pair be? Where do the asymptotes intersect here? X is 5, y is 4. Do you guys see the 5 and 4? Like, that would be like a test question, right? Hey, where do the asymptotes intersect? And then it would just be like an ordered pair. And then it tells me that you know where the x-axis and the y, the x equals 5 and the y equals 4 would intersect. Okay, that's it for, I think, 9.1. So I did assign homework yesterday, not yesterday. Yes, yesterday. Yesterday? Yes, yesterday. I did assign homework yesterday. I'm assigning, when am I checking your homework? Monday. And we're going to be done quite a bit more by Monday, okay? Double checking. Everyone got the 10 a week, yes? Okay. Okay, now we've got to take it to one more level of complexity. And this is why the second question I gave you guys at the whiteboards was so not okay. It's actually because I gave you something that had something called a point of discontinuity. When you guys were dealing with rationals last year, and you had something that looked like this, like if you had y is equal to, let's say, x squared minus 1 over, actually you didn't have y equals, you had something like this, x squared minus 1, and then x squared plus 2x plus 1. And you had these rational functions, yes? I need to make it different. Give me a second. X squared minus 3x plus 2. So this was a rational function that you guys would have like done a deep dive into, and you would have factored the numerator and you would have factored the denominator. And you would have said like, oh, okay, this is x plus 2, x plus 1, and you would have factored the numerator and you would have factored the denominator. And then you would have stated your NPVs. We don't call them NPVs in grade 12, okay? They're going to give us something different. So this is x cannot equal -2, x cannot equal -1. And then you would divide the common factors, and you'd be left with this as your simplified expression. However, you had to list both NPVs next to each other, right next to the simplified expression. So one of the NPVs is still there, and I can clearly see it, but one of the NPVs disappeared, right? But we still had to list it, okay? The NPV that disappears is going to become a point of discontinuity. And the one that stays is going to be your vertical asymptote. So last year, so many people were like, well, I only see the -2. I don't want to acknowledge the -1. The -1 means something. It actually gives you something different on your graph. Okay? So every NPV along the way matters. The one that's still visible at the end after all the simplification will be a vertical asymptote. The ones that disappear along the way will be called points of discontinuity. In calculus, you're going to call it a removable discontinuity. It's just a hole in the graph. Okay? So, yeah. Was it negative? Let's make it. Okay. There. Okay. So, what we're going to do now is, so a point of discontinuity describes an ordered pair. It's not just an x value. So grade 11, it was just an x value NPV. Grade 12, it's actually an ordered pair that's going to be a hole in the graph. And it causes a break in the graph. This occurs when you have a rational function in which the function can be simplified by dividing the numerator and the denominator by a common factor. We did this in grade 11. So the process here is going to be fairly straightforward. Now the result is a single missing point in the graph, which is represented by an open circle. A vertical asymptote is going to be that dashed line. The open circle is going to be a point of discontinuity. So the NPV, the factor that disappears, becomes a point of discontinuity. The factor that stays is going to be a vertical asymptote. So this is the graph. This is just like what your graphing calculator would have given you. Can I get you guys just to type this function into your calculator, just so you can see it, so you can see that it corresponds to this. Notice that the scale is 2, and so I had to use numbers and indicate that my scale was going up by 2 here. And we're going to graph this function. So, Hannah, can you read it to me? What was it? It's like x squared.
X squared plus 5x plus 6 divided by x squared minus 4x minus 21.
Okay, so if I wanted my window to look just like the graph there, maybe I'm going to make my scale 2 because it was counting by 2's, and then maybe I'll make my y scale as also 2, but then I can actually, okay, there's my function. Like I can see what we have there, okay? So what we're going to do is we're going to discuss the non-permissible values. So what we have to do, when you approach this, first of all, guys, do you guys see that the degree on the top is the same as degree on the bottom? Where's my horizontal asymptote? Y equals 1. So right away, I want you guys to put that in there before you've done any work at all. You approach the function from the front. If the degree on the top is the same as the degree on the bottom, you need to get your quotient of leading coefficients as your horizontal asymptote. So what we're going to do is we're going to factor the numerators and we're going to factor the denominators. What gives you a product of 6 and a sum of 5? Okay, so coming at this question, we've got y is equal to x plus 3, x plus 2. Now, what gives you a product of negative 21 and a sum of negative 4? Do you guys see the negative 7 and 3? Okay, for a second, turn it into a grade 11 question. State your NPV. X cannot equal negative 3. X cannot equal 7. Each of the NPVs is going to demonstrate something different, okay? So I know that x cannot equal negative 3, x cannot equal 7. These factors divide, which means this one is going to give me a point of discontinuity. Yeah? But it's a point. It's an ordered pair. So you have to write it like this, negative 3, and then I have to figure out the y value that I should never get. Okay? So that's one of the tricky parts, is people struggle with finding this y value. Now this is going to give me a vertical asymptote. And that's going to be at x equals 7. And we've already dealt with vertical asymptotes. How we find the y value of the point of discontinuity, you take your simplified equation. If I had put negative 3 back in here, it would have been 0 on the bottom, we would have been dividing by 0, and we would have been breaking math. If I put negative 3 in here, does it break math? It's okay for me to put the negative 3 in this one. This one, we would have been dividing by 0. This one, it's okay. So what we're going to do is we're going to insert the negative 3. The x value of the whole is going to go into the simplified equation. And I get 1/10. This is the y value that corresponds with the x value that we should never get. Okay? So we're going to get the y value by using the simplified. So simplified equation to find y of, and don't ever call it a P of D on a written response. This is just a thought process. I use the full word, point of discontinuity. Okay? But I use the simplified equation to find the y value of the point of discontinuity. So I'm going to put my details together. Hey, gentlemen, you're just being rude. Okay, x is equal to, stop talking. So x is equal to 7 would be your vertical asymptote. My point of discontinuity is negative 3 1/10. When you look at your calculator doesn't show you a whole. Okay? So trace 7, there's my asymptote. It won't give me anything. If I try to put the negative 3, was it negative 3 or was it 3? Negative 3, it actually gives me something empty. Like, so my negative 3 is right around here, but it actually won't give me a y value. If I go a smidge to the left, it does. If I go a smidge to the right, it does. Right? Like, I can move around it, but as soon as I try to put the negative 3 in there, so this is where you have to be smarter than your calculator. So negative 3 1/10. Okay? So negative 3 is right about here in 1/10. You have to put a whole, and you have to say negative 3 1/10. It doesn't matter which equation. You can use your simplified equation to get your y-intercept. Your y-intercept could come from 2 divided by negative 7, or it could be 6 divided by negative 21, because this would simplify to negative 2/7, right? You can use the simplified equation to get your x-intercept. You can use your simplified equation to get your y-intercept. Okay, you don't have to use the complex one, because these cancel anyway, right? So then it says algebraically determine the x-intercept. Let's do both. So we're going to use, for after we simplify, we're going to use this guy for the rest, right? To get your x-intercept, so y-intercept x is equal to 0, and I get negative 2/7. And then x-intercept, I put 0 in for y, and it's only the top factor that plays in. So then x equals negative 2. So right away, x equals negative 2, there's my x-intercept. I can see my negative 2/7. Now this is when things get pretty complicated. If you have no, like I would box the y-intercept, and if it's really hard to get it on there, then don't put it on there. And then I wouldn't write it like this. I'd be like negative 2 and 0, because x equals negative 2 implies a vertical asymptote. You got to give it to me as an ordered pair. So the only thing we're learning about today is pointed discontinuity. Now here's the tricky part. If I asked you for the domain and range, okay, so domain and range. Domain is easy. You would say x cannot equal negative 3 nor 7. For the range, you would have to say y can't equal 1 and y can't equal 1/10. The 1/10 is never going to happen. Okay, that's where the hole is. So you have to remember the y value of the point of discontinuity and the horizontal asymptote. Okay? Yeah? At the negative 3, 1/10? No, it keeps going. The graph keeps going. Because there's a non-permissible value here. X equals negative 3. It's an NPV. So if you look at the graph, so here we have it. It keeps going. It keeps going past negative 3. So it just won't give you a y value. And what your calculator can't do for you is figure out that the y value of the point of discontinuity was 1/10. You have to know how to figure that out. You take your simplified equation. You don't take the original, because if you put it back into the original, it gives you 0 on the bottom and it breaks math. But the simplified equation will allow you to find the y value that you're never supposed to get. Okay. So let's take a look at this guy. When you approach this from the front, okay, so look at it. It says, for the rational function, y equals x plus 2 over x squared plus 3x plus 2. Determine whether the graph of the function has an asymptote and or point of discontinuity. Guys, there's always multiple asymptotes, not always. So sometimes it's just a point of discontinuity, so I'll just take that back for a second. Determine the equation of the asymptote and or point of discontinuity. Sketch the graph of the function. I have that twice. Sketch the graph of the function. Sketch an accurate graph of the function. Okay, let's just get rid of that. A little repetitive. Okay, when you approach your function from the front, and you compare the degree on the top with the degree on the bottom, what happens? What do we get? When I look at the function and I compare the degrees, top is less than the bottom. Where's my horizontal asymptote? Degree 1, degree 2, horizontal asymptote is the x-axis. What's the equation of the x-axis, guys? Y equals 0. So right away, plot it. Okay. Now I have to factor everything. If I can't factor the numerator, it becomes its own factor. I factor my denominator. And you make sure your factoring is correct. From here, I state my NPVs. X cannot equal negative 2. X cannot equal negative 1. Yeah? Once I've stated my NPVs, I simplify. The factor that simplifies becomes a point of discontinuity. Now, if everything on the top divides, it divides to make 1. Make sure you put the 1 there. Okay? So now I know that this guy, this negative 2, is going to be the x value of my point of discontinuity, but I still have to find the y value that goes with it. Okay? the one that stayed, okay, so this is my new equation. I've got y is equal to 1 over x plus 1. This factor stayed on the bottom. That becomes your vertical asymptote. Yeah? Now, how do I find the point of discontinuity, the y value of the point of discontinuity? You take your simplified equation. If you would have put -2 back in here, you would have been dividing by 0 and your calculator would have freaked out for you. But our simplified equation, if I put the -2, actually maybe I should show it the simplified equation. This was my simplified equation. So if I put the -2 back in there, I get 1 over -1, which gives me negative, there's a hole at -2 and -1. So I've got my vertical asymptote. I've got my point of discontinuity. Do not call it a P of D. Do not call it a VA. Okay? I've got my horizontal asymptote. And then I have two more critical features, which would be x-intercept, y-intercept. There's no x-intercept. I've got an asymptote at the x-axis. There will not be an x-intercept. There is the odd time when it will happen, and I'll show you when that happens later on. But there is a y-intercept. You can take this one, or you can take this one. Your y-intercept, put 0 in for x, and you get y is equal to 1 over 0 plus 1, which is 1, and you write it as 0 and 1. So this is not a huge stretch, right? My horizontal asymptote is y is equal to 0. My vertical asymptote is x is equal to 1. Sorry, -1. My y-intercept is 0 and 1. This is really bugging me that it's so far over. I'm just going to erase that and start again. Okay. So there's my y-intercept. I have to put in a point of discontinuity. So at -2 and -1. So if this is -1, this would be -2. -2 and -1. I have to put a hole, and I have to label it as a full ordered pair. That's my point of discontinuity. And now I'm going to basically draw my curve. You're still getting infinitely close to, okay? But you have to make sure that you can see that there's a hole. Your calculator won't give you the hole. You have to be smart enough to know that, okay, there's a hole there, and I have to acknowledge that this was a point of discontinuity. So the NPV that disappeared in the process becomes a hole in the graph, point of discontinuity. Now, domain is super easy because it goes back to your original NPVs from grade 11. So you would just say x can't equal -1 and -2. X is an element of the real number system. For the range, there's two parts to it as well. There's y can't equal 0, but y also can't equal the -1, which was the y value of the point of discontinuity. So you have to put the -1 in there. And there's your rational function, domain and range, all the critical features. And you have to make sure that everything is clearly labeled. On this guy, I've kind of got plenty of room. I would probably like throw in the 0 and 1 as my y-intercept. I can see it. But you have to make sure that your hole is a clear hole and you've labeled it with an x and a y. Yeah? graph this. We're just going to talk about it. What are your non-permissible values of this function? Graph the numerator, factor the numerator, factor the denominator. State the NPVs, and then I want you to give me the feature exhibited at each NPV. Okay, the NPV of x cannot equal -7. Guys, which one is that going to be? Which feature is it going to be? Because this cancels, we know that this guy becomes a point of discontinuity. So it's going to be -7, but you have to find the y value that goes with it. A point is not a point unless it has an x and a y. This guy stays, so x equals 3 is your vertical asymptote. Guys, how do I find the y value of the point of discontinuity? Because you cannot say point of discontinuity without finding the y that goes with it. How do I do it, Ryan?
Sub it into the equation.
The simplified equation. Yeah. So I'm going to take that simplified equation. So it's going to be -7 minus 2, -7 minus 3. So this is actually -9 over -10. 2 negatives makes a positive, so 9/10. Make sure you put the 9/10 in there. Mine looks like a 16, so I'm just going to fix that. 9/10. Does that look like a 10 now? Okay. Domain. Super easy because it's just your list of NPVs. What's your range? Guys, don't forget that there is a horizontal asymptote at y equals 1. The degree on the top is the same as the degree on the bottom. So when you're finding your range, you have to state both the horizontal asymptote and the y value of the point of discontinuity. So any horizontal asymptote becomes part of the range. And then any y value of point of discontinuity. Okay, guys. Okay. Why don't you guys try this one? Analyze each function and predict the location of any vertical asymptotes. I'm going to cross off vertical asymptotes. I'm just going to say asymptotes because all asymptotes are important. Points of discontinuity and intercepts, and then sketch the graph. So just get like one step ahead of me. When you approach this function from the front, where's your horizontal asymptote? Degree on top is the same as the degree on the bottom. And we are going to state domain and range. Guys, if there's no constant term on the top, you know that that's 0, right? Like it'd be like 0 divided by 2 for your y-intercept. Or if you're finding your x-intercept, 0 here would just be x equals 0. So your x and y-intercept are one and the same. So make sure you're accurately graphing everything and labeling it. Guys, did you get -5 and 5/3 for your point of discontinuity? Okay. So make sure you're going through the 0 and 0 for your x and y intercept. And there's room to clearly label it. Make sure if you stop the graph at your point of discontinuity, if you don't keep your function going after the point of discontinuity, you'll lose half a mark. The point of discontinuity is not a stopping point, it's just one small break in the graph. Okay? And then just down here, quickly write your domain and range. And this is when you just have to be smarter than your calculator. Like your calculator won't give you the point of discontinuity. You can play with your calculator to get your asymptotes, but it's just so much easier just to get them properly. The detail people miss, they miss the horizontal asymptote and the y value of the point of discontinuity for the range. That's where people lose part marks on this question. Can you guys see that this unit would be like, it's kind of an easier unit? Yeah. Is there anything about this that doesn't make sense to you? You could type it into your calculator and you could trace the -5 and it won't give you a y value, so you know you're right. But you would type the whole original function in. Okay guys, try B. There's a black Dodge Ram truck in the parking lot with the lights on. Does anyone drive the black Dodge Ram truck? Guys, make sure you're always approaching it from the front and grabbing your horizontal asymptote right off the bat. Like, that should be the first thing you address. You done, Ansel? No, you're not. Go to the next one. You're just like, you're here to, like, just to talk to Vuyo. You're not here to learn. And I'm just like, Vuyo missed enough school. He does not need any more distractions. Guys, even after you simplify, your horizontal asymptote still indicates y equals 1. So if you do your horizontal asymptote before you simplify or after, it's still y equals 1. It's not going to change. Make sure you take your x-intercept into an ordered pair. Don't leave it as x equals 4, right? You think so? Remember, it could be any polynomial. So it could be a cubic function on the top. It could be a quartic function. Guys, just make sure you drew a curve that was diagonally across where the asymptotes intersect. Did you get 3 and negative 1/6 for the point of discontinuity? Okay, just make sure you give the domain and range. Most common mistake people make is when they're writing the domain and range for this guy. And it's not hard, they just forget that there was 2 y values. There's 2 y values that can't exist, the 1 and the negative 1/6. So domain is easy. The range is the piece that, like, I don't know, people just struggle with the range. And I hope that's not going to be you. Okay, are we good? Okay, so this one's going to look a little different. Okay, we're going to, yeah, we'll finish this page. Okay, so guys, look at this one for a second. The rule was if the degree on the top is less than the degree on the bottom, the x-axis is your horizontal asymptote. Or if the degree on the top was the same as the degree on the bottom, then the horizontal asymptote was the quotient of leading coefficients. If the degree on the top is greater than your degree on the bottom, there's no horizontal asymptote. So this is degree 2, this is degree 1. So I get to indicate no horizontal asymptote. Okay, so that's your first move. I'm going to factor this. This requires decomposition. So 2x squared plus 5x minus 3, what gives you a product of negative 6 and a sum of 5, right? So you've got like 6 and negative 1. So you can use your decomposition here. So 2x squared plus 6x minus 1x minus 3. When you GCF the first two terms, we get 2x. When I GCF the left, some people are like, Sakura, I have a feeling it's going to match the one on the bottom. So I'm going to guess and check what the other factor is because I have a feeling it's going to match. Okay? Some people don't use the decomp. Some people just like say, I think it's going to be x plus 3, and what would make the 2x squared happen? Put a 2x times x, 2x squared. And then they kind of mental math this. 2x times positive 3 would be positive 6x minus 1x. That gives you the positive 5. So a lot of people just kind of do the factoring by inspection, and they use, like they think logically about the factor on the bottom. Now guys, there's only one NPV. X cannot equal negative 3, and that factor eliminates. What we're left with is just this. That's not a rational. That's a linear function. Do you guys see that that's a linear function? So this is going to be a point of discontinuity. And it's going to be at negative 3 and some number. Let's figure out the some number. Y is equal to 2x minus 1. So y is equal to 2 times negative 3 minus 1. So this is negative 7. So I have a point of discontinuity at negative 3 and negative 7. Ladies and gentlemen, if you want to find your y-intercept, we know that the y-intercept is 0 and negative 1. If you want to find your x-intercept, put 0 in for the y. Guys, this is just a linear function. So I've got all this information. There is no asymptotes. There was no factor that was left behind. There's no asymptotes. So I have to plot negative 3, negative 7. So graphing a linear function, that's grade 10, right? Y-intercept, 0 and negative 1. X-intercept is 1/2. I'm going to make sure I go through that negative 3 and negative 7. I'm going to put my hole there. You could type this into your calculator and get more ordered pairs, but that should be more than enough. Whatever you do, do not stop at the point of discontinuity. Extends in both directions. Your domain is just going to be x cannot be negative 3, right? So when I'm dealing with this domain, x such that x cannot equal negative 3, x is an element of the real number system. The range, y such that y cannot equal negative 7, y is an element of the real number system. Okay, I want to show you guys this last question. Okay, you're going to match the graph with the function without using technology. So can I get you guys just to try this? So factor the numerators, factor the denominators, see if it's going to have a point of discontinuity. If there's 2 factors that stay, then that means that there's 2 vertical asymptotes, right? So factor your numerators, factor your denominators. And I'm not assigning more homework. Guys, do the homework from 9.1. Tomorrow you're going to get the homework from 9.2. We will finish 9.2 tomorrow, okay? If you want to start this homework, you can, but you don't have to.
On it.